All right, good afternoon. It's 12 o'clock, and it's time for the Iowa Learning Farms Conservation Webinar Series. I'm Matt Helmers at Iowa State University. I issue Extension and Outreach in the Iowa Nutrient Research Center, and it's exciting to be back on this week and get to hear about soil health and measurement across ag systems in the Midwest, or soil health, why and where. And so we are really fortunate this week to have Dr. Matt Ruark and Abby Augarten. I said it wrong. I knew I should have asked Abby before we started. So I apologize for how poorly I did there. Coming to us from University of Wisconsin-Madison. As always, if you have questions, feel free to type those in the chat box and we'll get those to our speakers at the end of the talk. So with that, I'm going to turn it over to Matt and Abby.
All right, thanks, Matt, and welcome everyone. Good to see everyone on this Wednesday afternoon. So we've been asked to talk a little bit about soil health and some of the work that we're doing at UW-Madison. And so the general title on, soil health management and measurements across agricultural systems. But in reality, our question is what to measure and why. And so we're going to focus primarily on that during our talk today. Now, Abby and I are going to be hammering through a bunch of slides and trying to get this as nice and succinct as possible. But really, this really could be broken into 5 or 6 different presentations. So feel free to obviously ask questions along the way. And Matt, if there's any really pressing questions, feel free to jump in, and we'll happy to answer those during the talk as well. Sometimes
okay, I'll do that. Thanks a lot.
Anyway, so and this is all part of. So we're here at the Department of Soil Science at UW-Madison. I also work for the University of Wisconsin-Madison Division of Extension, and a lot of this work that we're going to present today has been conducted as part of our Discovery Farms program. So today we're going to go through a couple different topics. So we're going to review the idea of soil health. Obviously, we always do that at the beginning of any soil health talk. I want to talk about interesting biological measurements of soil health. And then we're going to take a couple different approaches on how we're researching soil health. One is on this exploratory analysis on if these biological measurements have value. The second is utilizing long-term experiments that we have in Wisconsin. What do they reveal? And as we get into it, we're also going to talk about, in the context of soil health, the idea of subtle shifts in management versus system shifts in management. And then lastly, we're going to take a deeper dive into pastures in soil health. And so we just want to highlight this large range of soil health research we're doing. And if there's any one particular topic that's of interest to you, let's start some chatter on those topics. So everyone has seen this slide, right? What is soil health? That combination of physical, chemical, biological properties. But the way I like to discuss this is that within each fraction, we have all these things that we can measure, right? And when we break things down into the chemical fraction, physical fraction, biological fraction, the chemical fraction, well studied. We've been studying this for, over a century. They're relatively easy to measure. A lot of these measurements are incorporated into soil test labs, things like pH, soil nutrient levels. Physical properties, also well understood. They're often things you can see, but are hard to measure. Not hard to measure is maybe not the right term, but cumbersome to measure. We can't necessarily conduct it in a soil test lab. But these are like infiltration, aggregate stability, electrical conductivity, the idea of erosion rating or compaction, things that you can sometimes visibly see. If you have poor infiltration, you're going to be able to see it. Lastly is this biological fraction. And we talk about this, I put not well understood. There's still a lot of investigation into this area of soil science or soil health. Easy to measure. Some measurements are, some are pretty cumbersome. And then the idea of what should we measure. And so as the science of soil health is advanced, it's really this biological circle that where there's a lot of research opportunities and things to discover. And we need to say that to note that soil health is multivariate in nature. We're not promoting measuring one thing. It's probably going to be a collection of things. We're probably not going to be able to sum it up with a single number. But as we move forward here, we are going to focus in on these biological measurements to figure out where which measurements are going to be interesting to measure and what value they may provide. So this ties in. So once we think about soil health, this really makes our discussion of soil health maybe more about soil testing than it is about soil resiliency. So what makes a good soil health indicator? So something that can be rapid, reproducible, and relatively inexpensive. Basically something that can be performed in a soil test lab with a quick turnaround time. It needs to be unique, and I use that term to mean basically it can't be too strongly tied to another measurement. And specifically, we're always measuring soil organic matter as part of a routine soil analysis. Do these just reflect, higher or lower levels of soil organic matter, or can they tell us something in addition to that measurement? Needs to be sensitive to management. Can't change the value, then it's not a good soil health indicator. And also, it needs to be connected to something of value. And there's a lot of different things where we can put under the value. And we'll show some data on some of the work that we've done on that. Okay, so the first thing we think about, what should we measure, right? So there's two types of measurements that have been identified that can be valuable in soil health testing that connect to the soil biology. One are incubations. So there, we're going to take soil, we're going to let the microbes do the work. The microbes are going to, so we basically take soil, we incubate it for a certain period of time, and we measure either the carbon dioxide coming off or the nitrogen that's mineralized. So that can take 24 hours. Some tests go maybe up to a week. The other one is an extraction. So this would be more similar to, we take the soil, we extract off a carbon or nitrogen pool. Not too dissimilar than, our potassium or our phosphorus tests. So it's going to remove a pool of carbon. It's simple, it's rapid, and usually we use a colorimetric approach. So these fit really nicely into soil test labs. Okay, so what are these? And maybe if you've seen any other soil health talks, you're a little bit familiar with them. But this is how we've been breaking them down. We've got the incubations, or we got the extractions, and we're pulling off either a carbon pool or a nitrogen pool, or measuring a carbon or nitrogen pool. So for carbon, the chemical extraction is that permanganase oxidizable carbon. Sometimes you've heard that called active carbon. It's a colloquial term. POX-C is what we're going to refer to it during this talk. The second one then for the incubation is going to be the potentially mineralizable carbon. You may have heard that as soil respiration. If you've used Solvita is kind of the take-home test kit of this. We're going to call this mineralizable carbon, or Min-C. For the nitrogen pools, we can extract the soil protein pool. ACE protein or soil protein is sometimes what we refer to that as. And lastly, for an incubation, we can pull off a potentially mineralizable nitrogen pool, so the PMN. Let the microbes incubate for a certain period of time and see how much nitrogen mineralizes. And so of these four, they provide kind of that nice balance of carbon and nitrogen, extractions and incubations. And those are the ones that we're going to focus on in our work. So our approach then to studying soil health in Wisconsin is, so there's two aspects of this. We're going to survey farm fields, and we're going to utilize long-term experiments to understand how both management and inherent properties affect soil health. And really, we want to address this idea. So when in all this discussion of soil health, there's the discussion of soil health is related to increasing carbon inputs into soil, diversifying the carbon inputs, and reducing soil disturbance. And what we want to address is, does this narrative hold true in Wisconsin? And we're going to use this approach to work to discover that. All right, so the initial exploratory soil health work in Wisconsin was conducted through our Discovery Farms program. We started in 2015, so across 2015, 16, and 17, we surveyed farm fields. So this type of work has no experimental design. We worked a little into Minnesota as well. But we just found all farmers, we have these regional networks of farmers. We asked if we could soil sample on their field, and they let us. We have 218 fields across those 3 years. But not only did we analyze the soil for all those soil health metrics, we also got all of their management information. That was a key thing. So for farmers to participate, they had to give us all of their history of farming practices. We typically collected early in the spring, and we always collected this is based on a 6-inch soil sample. So as we look at all these variables, there's all of these things we can study. So on the left, these are the soil properties, right? These are these inherent soil properties. And also we have some regional and seasonal stuff. But the two big ones that we're going to focus on are texture class and drainage class. So something that's related to the texture, things we think, the ability to higher clay content, the greater ability to hold on to carbon, perhaps carbon fractions. And drainage class is important, the amount of water that will exist in the soil at any one time. We're also interested in management practices. Here we have a lot more of things to consider: the tillage, the crop rotation, manure inputs, cover cropping, other random things, tile drainage, if it's irrigated, how much nitrogen they apply. So we collected all this information that reflects short-term and long-term aspects of their management. So the first question we had asked, right, are these just fancier measurements of soil organic matter? And what we want here is we do not want these to be too associated with soil organic matter, too correlated or connected. And here we're using regression analysis to identify what % of the variation can be identified. And you can see that on the x-axis, this is soil organic matter. Each data point here represents an individual farm field. And then we have POC, which is the extraction. We have mineralizable carbon, mineralizable nitrogen, which are the incubations. And so you can see the R squared for the POC was 0.61. So it was a little bit higher, but the soil organic matter only represented about 60% of the variation. Everything's generally positively associated, but there's still a little bit of variation left over. For the mineralizable carbon and mineralizable nitrogen fractions, those were much less explained by soil organic matter. So what our loose interpretation is here is that these R squareds are not 0.8, 0.9. It's not completely controlled by organic matter. There is these are providing these values, these measurements can still reveal something extra about the soil other than just the soil organic matter, or beyond just soil organic matter. So that's good. Didn't have myself here. All right, so what about these other inherent soil properties? So we talked about drainage class and we talked about texture. So this is kind of we'll go through this a little quick, but as on the drainage class, as we're working left to right across the graph, we're going from poorly drained soils to well-drained soils. And the big factor here, or this was a big effect for POC as we made the soil, or as the soil was naturally better drained, the POC actually reduced. Or so on the flip side, the more poorly drained the soil, the greater the permanganase oxidizable carbon. And so this does kind of make sense because as the soil is more and more poorly drained, we have a greater ability for that the organic matter to accumulate and organic matter pools to accumulate. Obviously, the most extreme example is a wetland soil, right? When we look at the texture, we're seeing the effect of texture, also primarily on permanganase oxidizable carbon. Here, we're working from sandy soil to higher clay soils. So from left to right, we're increasing the clay content. And with an increase in clay content, we say greater permanganase oxidizable carbon. So, and the effect on the mineralizable carbon pool, the extractable pools, was only really seen at the extremes. So it really seemed to have a big effect on that POC. So maybe because it was a little bit more strongly connected to organic matter. So better natural drainage, less POC, sandier soils, less POC. So what does this mean? This means as we start to expand out our benchmarks and our interpretations of these soil health metrics, we do need to have some inherent soil property considerations in it, right? If you have soils of contrasting texture, they will have that fact alone will affect the amount of POC that would be in those soils. So it's been doing a little drawing here. We'll fix that later. All right. So what about management? And so we did all of this analysis. We can do all this fancy statistical analysis, throw everything into a model. But at the end of the day, there was one factor that was consistently had the biggest effect and the biggest controlling effect on the amount of OxC and mineralizable C, these biological indicators of soil health in Wisconsin. And that related to crop rotation, and specifically the crop rotations that had more biomass, that produced more biomass. So we have perennial legume rotations. These are going to be like your typical corn alfalfa rotations, or ones that were in continuous corn tended to have higher values. So let's start with this perennial legume. So what's special about a corn alfalfa rotation? Well, we have that aspect of perenniality. Alfalfa is being grown, 2 to 5 years in rotation, across the rotation. No annual, there's not annual tillage that's occurring. It has a high amount of biomass return. These are high biomass crops, especially for alfalfa when you consider the amount of root biomass that's being added into the soil. Additionally, because corn alfalfa rotations are tied with dairy production systems, it comes with manure. So not only do we have an increase in perenniality, we also have these manure additions that are happening. On the flip side, what's special about a corn-on-corn rotation? So in this context, it had been continuous corn for at least 5 years, but usually this would indicate that it is primarily corn in rotation. Well, one is as a higher biomass return to the soil, corn stalks having more carbon return to the soil than soybean or small grains. So that's one effect. But also the aspect of there was a regionality to where continuous corn was being grown. We don't know if this is a cause or the effect. Is it because soils with greater inherent soil health or higher organic matter were the fields where farmers could push that and keep continuous corn growing? Or is it the effect of the continuous corn? So, some of our thoughts are, well, it may be likely that fields that are, that have higher organic matter are ones where farmers are more likely to grow continuous corn as well. So we can, with this kind of analysis, we can't separate necessarily the cause and effect. All right, so what about things that matter? So in the context of things that matter, we looked at yield. And so at all of these sites, we also got corn yields from these fields. And this is another case where this type of analysis is very messy. We take all the data, we throw it into a big statistical model and see what spits out. And apologies for the metric units here, but this is in a recent paper that we published so we were able to look at, even though with all this variation, we can use these models to look at how does organic matter affect crop yield. And we also compared it to the permanganase oxidizable carbon and the mineralizable carbon. So the first thing we see is that we are seeing an increase in organic matter. As we see an increase in organic matter, our models demonstrates that yields do increase. Now it does start to taper off once it gets above 4%, but as it shows, building organic matter up to 4% leads to greater yields. Now this is similar to a recent global review that also showed corn yields increase with organic matter up to 4%. So this, to me, that demonstrates that there is clear value in wanting to build organic matter in that upper 6 inches, in that upper plow layer, because it does have a positive association with yield. Interestingly, we also saw that a clear effect for mineralizable carbon. The effect was not as pronounced, although it was positive associated, but not as pronounced for permanganase oxidizable carbon. So this is not the last data set that we're going to look at when it comes to yield, but all of this data does push us in the direction of, yes, that there is value in increasing organic matter. There is value in potentially increasing these soil health metrics. So just to put a final little summary on this exploratory analysis, and I really cannot highlight the term exploratory enough, right? This is on-farm, survey-based approach, right? We identified those incubations and extractions that we think are going to have some value, and then we can answer these questions. Do these measurements add new information about the soil? And the answer is yes. It does not just simply reflect organic matter. There's a lot of variation left over. However, they were tied to texture and drainage. So there's other inherent properties to think about, and if we're benchmarking it or eventually creating any sort of recommendations related to soil health. The second, is it connected to management? In Wisconsin, yes, but specifically it was related to biomass input, the amount of carbon returned to the soil. Those other management practices in the context of our data set were not as important. And lastly, Is it connect to anything important? And yes, yield. So as we move forward, we feel that these are good biological indicators for these reasons, and we're interested in exploring this more. So with that, I'm going to turn it over to Abby, who's going to continue some of the discussion related to our long-term experimentation and then comparison of a broader comparison of our agricultural systems.
Thanks, Matt. So I'm going to dive in a bit and talk about long-term cropping system trial, some data from a long-term cropping system trial, which serves as a great complement to that survey exploratory data analysis approach. So in Wisconsin, we have an integrated cropping system trial in Arlington, Wisconsin. In the soils map on the left, you can see that it is located on a mollisol soil type that is highly productive and resembles a lot of the soil types found in Iowa. And this is a 30-year long trial, and it's looking at 6 different cropping systems. So rather than looking at the effect of any one management practice, we really want to evaluate common cropping systems throughout Wisconsin. So there's 3 cash grain systems, a continuous corn system, a corn-soybean rotation, and then an organic grain system. And then 3 forage systems, one being conventional, one organic, and then a pasture-based system with well-managed grazing. And a couple of years ago, there was a soil health assessment on this cropping system trial to evaluate how these biological soil health measurements may vary based on system. And I'm going to walk through the average values from that. So the first is POC, which is that active carbon pool that Matt was talking about. And we see a clear shift in values as we move from those grain systems to the forage systems. So while there isn't a lot of variation within the 3 grain systems, we do see this stepwise progression as we transition to forage systems. Similarly, when we look at mineralizable carbon, which is that incubation, we see again that stepwise progression. And then additionally, we see another leap when we move to pasture. So not only was there an increase in NINC in those forage systems, but then when we move into pasture, those are also higher. And then for potentially mineralizable nitrogen, we see this same trend. And this makes a lot of sense given that those forage systems have alfalfa in the rotation. They often are accompanied by manure application. So they have, diversity in the crop rotation, that element of perenniality, as well as manure organic inputs. And to build off of our survey work that Matt had shared, we created a similar study to evaluate pastures, which have been underexplored in soil health. So last year we sampled across nearly 100 pastures in Wisconsin, focusing on 2 geographic locations. The first being in the driftless area, which are the dots in purple, and then the second being in the north central area. And to participate, the pastures had to be at least 1 year old. But after that, the goal was really to cast a wide net and capture a lot of variability. So a lot of variability in the age of pasture, land history, soil types, as well as pasture and grazing management. And then there's 2 benefits of this study. The first is we can utilize this data to compare it to previous survey work that was conducted on cropping systems. But then we could also delve into the pasture-specific data set to tease out trends as to what most influences soil health. So tackling the first goal of comparing across systems, we divided the data into 3 major cropping systems. The first being solely annual cropping system, which is in red, then an annual and perennial system. So these include alfalfa in the rotation and are often accompanied by manure applications, and these are in green. And then lastly, the pasture systems are in blue. And for this, there's a graph for all 4 of those biological soil health indicators of interest. And these are distribution graphs. So on the x-axis is the value for that specific soil health indicator. And then as you move across or move through the distribution curve, at any given value, the amount of sites underneath, or the curves represent the amount of sites at that given value. So you do see that at the extreme values, there tend to be fewer sites, and then most of the sites have, the typical average in the middle. But what's really important and interesting here is to see how the curves parse out based on that cropping system. So as you shift from the annual system to the annual perennial system, that curve slightly shifts up, indicating higher values. And then in the pasture system, that's an even further shift. And for epoxy in that upper left corner, this trend is a little bit less defined. But when we look at the other indicators, so this is ACE, so that's soil protein, that shift becomes more defined. And then the biological incubations, these systems really do parse out. So overall, we observe that greater soil health measurements in those systems with perenniality and organic inputs. So this really reflects and bolsters what we saw at the Wicks trial. And seeing that pastures parsed out as having the highest biological soil health values, this does make a lot of sense. If we look at NRCS's 5 criteria for soil health systems, pasture systems inherently check off all of the boxes. So there's very minimal, if none, bare soil. So there's adequate soil armor. They minimize soil disturbance. There's hardly, if ever, a tillage pass. There's ample plant diversity by incorporating both grass and legume species at all times with a variety of species within that mixture. There's continual living plants and roots. And then lastly, you have that component of livestock integration and that manure and nutrient deposition from having active grazing. But if we look specifically within the pasture data set, we can ask among pastures what influences soil health. And what we found was that pasture age is the main driver of soil health. So these graphs on the right, there's one graph for each of our 4 biological soil health indicators of interest. And we see this strong positive relationship where as pasture age increases, we see higher soil health values. And this is really important because not only having those beneficial soil health practices can lead to higher soil health, but just the duration of time that those practices are implemented on the landscape is significant. And in this data set, the R-squared values show that 20 to 30% of the variation in these soil health values can be attributed to pasture age. So this is a really important effect. But there's a lot of values and factors of interest. So looking specifically for rotationally grazed pastures, we wanted to evaluate what influences soil health values, including both inherent soil properties and management. So for soil properties, we have pH, soil texture, and drainage class, which Matt showed earlier to be very influential on previous soil health work. And then we also have a lot of management factors. So we have pasture age and previous land use that can't necessarily be decided upon by a land manager. But then we have a lot of different rotation factors. There's components of stocking rate and density. So the grazing pressure for any given grazing event. There are inputs of fertilizer and manure, other practices like haying, and so forth. But these are a lot of variables, and evaluating each variable individually won't really paint the picture of relative influence. So we can use statistical approaches like random forest to help us analyze data sets like this. And what a random forest does is it gives you the relative importance of each variable and ranks it so we can start to discern how each of these variables may influence soil health among pasture systems. So I'm going to share some data for epoxy and MNC. And just to orient you to these graphs, the variables at the top are those with higher influence, and then they go in decreasing order. And the bars themselves represent the relative influence. So you could compare each bar to the other variables to see the magnitude of that relative influence. So we're looking at epoxy on the left, which represents that active carbon pool, and then mineralizable carbon on the right, which serves as that proxy for microbial activity. And this shouldn't be too much of a surprise, but pasture age was the most influential variable for both of these indicators. And then if we look at texture, which we know to have a high influence, we really saw these being influential for mineralizable carbon. So they were the second through fourth most influential variables, looking at that percentage of clay, sand, and silt, where sandier soils have lower values, and as you increase the clay content, they typically had higher values. But for epoxy, it was much lower in terms of relative influence and didn't really tease out as having a main effect in this data set. We then can look at grazing management factors. So for epoxy, stocking density, which represents the grazing pressure for each grazing event, and then time in paddock, which is how long the livestock are on the given paddock before rotating to a new pasture. Those were the second and third most influential variables in this data set. And for Mincy, time in paddock came out right after those texture variables. So this is really interesting and exciting to see how grazing management does parse out and how they may influence these indicators or be related to the indicators. And lastly, I do want to point out that for epoxy, pH was a significant effect, specifically that higher acidic soils had lower epoxy. So overall, I think the main takeaways are the large effect of pasture age on these indicators, and that as these soil health principles are applied to the landscape over a longer duration of time, we do see soil health benefits within these metrics. And secondly, there is a role of inherent soil properties that need to be accounted for a given producer to interpret soil health values moving forward. And lastly, that grazing management does play an influence and a role on these indicators. So circling back to this hypothesis that improving soil health is related to increasing carbon inputs, diversifying carbon inputs, and reducing soil disturbance. And we asked ourselves if this narrative holds true for Wisconsin. And overall, we say yes. We really observed that as we shift systems from grain to forage to pasture, this opens up a lot of opportunities to apply these soil health practices to the landscape. And as a result, we see increasing biological soil health. Specifically, when we look at pasture systems that are pure perennial systems with a lot of crop diversity and manure inputs, and forage systems, there's still a lot of opportunities for that. Perennials in the rotation, opportunities for manure, reduced disturbance when it's in that alfalfa crop. And then in grain systems, grain systems are a little bit more confusing. There's still a lot to research and better understand, but we believe that as we try to work within grain systems to mimic perhaps some of those other systems and include greater perenniality and living roots and crop diversity and carbon inputs, that there's the potential to increase soil health values. But there's also a need to collect more data and expand our data set to start to tease out the effects. There are opportunities in grain systems for cover crops and reduced tillage, but really exploring how to best implement those practices and will they result in measurable increases to these indicators. So with that, turn it back over to Matt.
Right, thanks so much. Okay, so the logistical items here, if you are on this webinar and would like or need a CCA CEU, please email Liz Ripley with the email as shown there, ejukums@iastate.edu by today at 5 p.m. and include your name, the name you entered to watch the webinar, and your CCA number. And then feel free to type in your questions. And the last slide, or the next slide, is put a plug in for the webinar next week. I think we have Chad Penn with USDA ARS, research soil chemist, there to talk about phosphorus removal structures, an overview of utility and limitations. Okay, so with those done, we do have some questions that have come in. And first one here is, do you do any in-field infiltration test or lab KSAT test in addition to some of the testing that you described here?
So in terms of the physical property stuff, we had started, our original plan was to do a lot more of analysis. And what we found with the infiltration was that we would do multiple spots within the field, and our variation was quite high, and we just struggled with that the entire first year. And so we sort of abandoned that as a rapid test. And so we do think that we have tried on the physical side, we've moved towards some of this aggregate stability, a wet aggregate stability, with this Cornell the sprinkle infiltrometer, right? So that's something that could be incorporated more into a soil test type approach, but we're just scratching the surface with that type of analysis. But I would love to see more physical properties incorporated into our rapid assessment of soil health, because clearly the water aspects and the ability to store and move water into soils is a huge component of this.
Yeah, that's certainly been our experience as well. That infiltration is so variable. I think Eric Henning is on here. He's done some work with prairie strips, and we see a lot of variability in that infiltration. But the wet aggregate stability is where we maybe see the early indications of some benefits kind of from the soil health standpoint with that. So. Next question, did you look at the effect of manure type, liquid versus solid manure, on soil health?
So that was one, there's all these things that sort of didn't come out in our models. We have, and are basically the reasoning, a lot of the reasoning for it is because we didn't have as big of a range in those factors, right? So even when we had, 220, 225 data points, we didn't have that. Most of the manure was liquid dairy manure. So we didn't have that range of data. So that it really highlights, as we expand out data sets like this, we need to be we need to set those as priorities. Like, that is one clear thing that we could not pull out that we noticed, the idea of source, and that, like, in a more controlled setting, we may find that to be true, right? The idea of liquid manure versus solid manure, but in the context of our data set, we couldn't identify that. And just along those lines, if I follow up, also the idea of tillage was not pulled out in our data set, but that effect was such a regional effect. So the southwest corner of our state, the northeast corner of the great state of Iowa, driftless region, right? So highly erodible landscapes. The vast majority of our no-till sites were in that region, and those sites had inherently lower organic matter. So we couldn't connect tillage to organic matter in soil health in the context of this study. So there's some drawbacks to our approach. We need to certainly expand it. We need to go from hundreds of data points to thousands of data points. But there's anyway, so it's just a limitation of our approach.
Okay. Great. There was a question, if you could put up your contact slide again.
Yes.
Hey, this one, right. A few good questions have come. All of them are good. So, but this is one that I should say, this is what I pick of and maybe gets at the heart of a lot of questions on people's mind, I think, nowadays. So you've demonstrated lots of opportunities to use changes in management system to improve many soil characteristics. How much opportunity do you think there is to use the changes in management practices to add significant amounts of carbon into the soil?
Yeah. So our context here is a soil health, soil organic matter at the surface horizon context, right? So the idea of if it's about adding significant amounts of carbon to the soil, if the question pertains to the idea of carbon sequestration, I'm gonna kind of chicken out and basically not address that, just in the context because we didn't measure deep carbon, okay, right? So if the idea is how to incorporate significant amount of carbon to try to build that surface organic matter, then it's going to come from, we have to figure out how to make our annual cropping systems look more like our perennial cropping systems, right? So how can we do that? Can we get more cover crop biomass in? That's going to be a challenge in our high production systems where we're already utilizing all of our, growing degree days, all of our photosynthetic activity for our cash crop, right? So how much are we going to consider leaving left over for a cover crop to try to grow more biomass and put it into the soil? Can we start to access manures from different types of cropping systems into our annual cropping systems? And then in the context of all that, reducing our tillage. So there's a great challenge. That's a grand challenge for our systems in the Midwest that are primarily corn soybean. But if we do it, and also as we do it, we also have to give it time, right? These are long, the buildup over time is we're probably looking at a decade or more to see meaningful changes. But most of the work shows that directionality is correct. If we can do this and commit to it over time, then these improvements will come. That's my spiel on it.
Okay. So next one is you tied soil health to yield for the grain systems. Did you consider tying soil health to biomass production for those forage or pasture systems?
So that's also been a grand challenge, and I don't know if you would like to address the pasture system.
Yeah, I can address the pasture systems. It was definitely our intention to get biomass and productivity measurements. It is a lot more challenging because you can't just grab data from a yield monitor. So specifically for like those rotationally grazed systems, the intention was to get pasture stick measurements before and after each grazing event. But yeah, I mean, that's asking a lot of producers, or you have to assess fewer fields so that, I could collect all that data throughout the growing season. So not for lack of trying. I think it is incredibly important to, again, look at that link between soil health values and productivity or other ecosystem services so that you have that so what factor. But I think it's a lot harder when you're thinking about biomass, especially when it's being rotationally grazed. So, yeah.
Big challenge for us. We're working on trying to address that. And everything, and then the context of other forage systems, everything that we did, every other field that wasn't pasture was collected in the corn phase. So we collected that soil sample in the spring, and we had the corn yield in the fall. So we didn't include any other yield metrics other than corn.
Okay, great. So there was quite a comment, and then question. There was quite a lot of noise in the relationship between the biological test and yield. Any thoughts on kind of why there might be that much noise in it?
And so, and it kind of gets to, and this kind of gets into some of, if anyone's really interested in getting to some deep statistical discussions. But our approach, we took what we call maybe more an approach that ecologists use, so we have this unstructured sampling, but we have all of this data, right? We had 27 input variables that we could put into a linear mixed model, right? And then so what we can do is we can figure out which variables in those models were important. And for example, soil organic matter was a top variable in terms of relative importance in that model. And then so what we simply did, there was a lot of variation, but then we can basically use that data set to construct a model to explore how that relationship looked by holding all the other variables constant. And so when we create that curve to look at that effect, it's holding all these other effects constant. So it's all of those, like there's a lot of factors that go into controlling yield. And so what we basically, it was just like, I don't know if that makes any sense. I would say if anyone, I'm happy to share a link to the paper if anyone's interested in reviewing that and seeing how we explored that relationship. But basically, we constructed a model, but it's not a mechanistic model, right? We just let the data drive it. So I'm not sure that makes any sense, but if there's other statistical experts that want to chime in and discuss it too.
Okay. Great, thanks. One more here. Still got some time for a question or two, but and I think another good, maybe challenging question. But how much increase in organic matter is needed to, I guess, to show a significant enough change in carbon to affect soil health and crop yield? So, kind of what might be the significant enough change in carbon to positively affect soil health and crop yield? And probably it depends on where we're starting and so forth. But I guess any thoughts on that one?
Okay, that is a great question. But I guess it does tie to that previous question of that's kind of where we may stop in terms of our predictive capacity, right? There was a lot of variation in that data set. We're using that statistical tool to show that relationship between organic matter or those, soil biological values with yield. We feel confident that it's positively associated, and we feel strongly that the biggest increases occur, between that 1% to 4% range. Above 4%, the data gets a little sparse. So it's right now, I would leave our conclusions as that it's worth attempting to increase your soil organic matter and soil health, but we also need to. Then that puts us back into that aspect of, okay, but we also need to understand the capacity of soils to build carbon based on drainage and based on texture. So I don't have a specific answer to that question, but I believe I'm hoping that we can move in that direction. That would be as we build out these data sets, we can work towards answering that question.
Well, I think I'm especially interested in some of your your first graphs that kind of looked at some of these variables as we think about kind of some of the inherent soil properties of soil texture, drainage, class. I mean, I think we need to take some of that into account
Right.
as we think about this soil health and what's the potential for increases, and understanding that some of these systems start off a little bit different because of how they were formed initially. So.
Right.
I think that's all the questions, and I think so you can
There's a couple format in the
okay, great.
direct
you
message
got?
to me. I don't know
Okay.
if that's if the people are comfortable with me addressing these.
Yeah, I think so.
But,
that sounds great.
There was a question about, did the research take the impact of how we added fertilizers and herbicides, or how the cover crop was planted. And so we did have the idea if it was manure or fertilizer. That didn't come out as a big effect, but we did not have herbicides as part of our inputs. The killing of the cover crop, again, that's one where we actually didn't have many sites that had cover crops. And if they did, it may have just been for 1 or 2 years. We were really, lacking that long-term effect of cover cropping. So unfortunately, we weren't able to decipher that. But again, I still think that the overall message does tie to what the value of the cover crop will be. If you can get more biomass into your soil over time, that could have that benefit. And then lastly, there's a question that we demonstrated lots of opportunities to use changes in management systems to improve many soil characteristics. How much opportunity is there to add? Maybe this was the question.
You did.
Sorry.
Yep.
Okay. Sorry, Matt. I always like to answer Matt Levin's questions twice.
Right.
So.
Yeah.
And I'll probably have to email him later once I think more about it.
Think about you. You'll wake up tonight being like, okay, this is how I should. This is an answer there.
So the answer, I guess, now I'm reading it, right? Like the answer is, if you really want to increase significant amounts of carbon, then you got to go to a perennial system, right? It's just there's the physics and the biology involved push towards that. That's the pathway. If the goal is to really build carbon in soils, we have to go to those systems, right? So as we work within our annual grain-based systems, it's the great debate is like, how optimistic should we be that we can do it, right? And how much we know what all the challenges are of how to get more carbon in there. And so the question is, can we do it or not? And then what do we have to sacrifice when we do it? We got to give up some photosynthetic activity for that cash crop. Does that come with less yield? or not. So
Great. But lots of research to do in this area for sure.
maybe just a little bit.
Maybe just a little bit. We all have job security, right? So, all right, Matt and Abby, thank you so much for participating today. And we will hopefully maybe get you on at some other time in the future. And with that, I think we will say thanks unless there are any last comments, Matt or Abby, that you want to make.
No, and if anyone wants any, I'm happy to share any of these slides, of course, or any of the other materials. So if anyone like any of this, any information, feel free to contact me directly. Otherwise, if you're interested in that paper that's on organic matter and yield, it's in Soil Science Society of America Journal in the past year. Emily Oldfield is the first author.
Okay. All right. Well, thanks everybody. Thanks for attending today, and thanks for the great contribution, Matt and Abby. I wish everybody a good day, and hopefully we'll, at least in central Iowa, we'll go a couple days without rain so we don't get worse flooding.
Good luck. Yeah.